Hello. In this video, I want to give a brief introduction to defects in nanomanufacturing. So there are many different kinds of defects in semiconductor manufacturing here. So as we pursue the Moore's law and the nodes getting smaller and smaller, defectivity is one of the main technical challenge here. In the first page here, I show a few examples of defects. I will talk about each of them later on. And here's my outline. In this video, I want to start with what they are, what's the typical defects and their impact. And then I will talk about where they are from, the origination. After that one, I will focus on, so this is the first, this is the first part and this is the second part. I will discuss on how we can see it, the defect inspection, and finally, some possible way we can resolve them. So the first typical type of defect is particle. Particle is a very general way to describe some small defect. It may be different material and maybe different shape. It doesn't necessarily to be spherical. It can be any ugly shapes, and it doesn't matter for where is the location. It can be on the bare silicon wafer, can be a gate or oxide layer, can be in an interconnect. And this one can particle defects can be like a contamination or a follow-on materials and other types. Usually we name it particle because they are small. Actually, for many years, semiconductor companies have been focusing on this type of defects, because for large defects, which we'll talk about in the next slide, like some big scratch or like a big watermark from immersion, those are very easy to identify and relatively easy to resolve. But for small particles, for small defects, those particles, they are really much more difficult to see. Even though they are small in size, it doesn't mean the impact is small. It can be minor, it can also be fatal. It really depends on what's the material and what's the size. So here I show an example SEM image. A large particle here, it's a very large one, it's more than 1 micron. We call it large particle. For this one, it calls a 3-line open circuit. And for the second one, it's a very small particle here, but because it's connecting 2 lines, a small particle of metal contamination, it can causing lines short. For both cases here, they were causing the design not working. Also, small is a relative term. As the nodes get smaller and smaller, here we got the familiar picture from Intel. Say if we have a 20 nanometer particle here, for 90 nanometer in 2003, it might be doesn't matter. It might be just a small dot in the gate. But for the 32 nanometer or even 22 nanometer, you will have a huge thing here. It will be comparable with the nodes, and then it will become a very critical for current node. So there are also many other typical defects. For example, it can be residue from the liquid. There are many in the process. There are many ways we will use some liquid. For example, the wet etch or the CMP or water immersion. And also there, so this is the residue from the liquid. There are some slip lines. So this is the slip line here. They are usually very large and usually on the wafer edge. There's some scratch, a huge one here, or some micro scratch. There's a small one here. And it can be bridging, maybe from the exposure. Here is an example from the under exposure. There's a ring here, under exposure. And there are some epi-silicon stacking fault. We learned from the class, we will have some epi-silicon growth in the FinFET. So if there is a stacking fault because the crystal growing with maybe a layer wrong, then it can cause a problem for the FinFET. Some other, like the resist, have some embedded defects here. You can see in this is the resist, and it can causing a lot of problem. And also some other defects like the line width roughness, the overlay error, and so on. So for the root cause of the defects, so where they are from, some defects are from the wafer manufacturing. When we get a wafer when we buy a wafer, supposed to be a clean wafer, but not exactly. It's never ideal, right? So some small particles on the bare silicon wafer can be a big can be a disaster. For example, here is an example here. Bare silicon wafer, this is a bare silicon wafer, and this is the pattern wafer. So a bare silicon wafer particle can causing a big bridging after it is patterning. So this is from the wafer itself. However, for most times, the defects are added during the process. Because we have so many different processes, we have over 150 steps and many different layers. So there are a lot of process we can causing a lot of particle or a lot of other defects. So we have physical contacts can induce some contamination. We have the air or liquid movement, and there's some condensation or electric spark or arcing, and plasma discharge and chemical corrosion. So for many of the processes, they can cause a lot of defects. And there's another very important source. The defects may be reproduced from the mask. So if the mask, or say the reticle, has a defect, then it will print on the wafer over and over again. So it will reproduce on every single chip. That's another way where we can get the defects. It's from the mask. And also, as we said, it's from the process, but for each process is not only generate one kind of defects, it can generate multiple. So here I give an example of the CMP. So CMP, the chemical mechanical polishing, we learn from the class. After we have the oxide or any other metal layer, we cut it flat or we polish it flat by the CMP. So CMP is actually really a dirty process. It has physical contacts. It has all of those slurry, and has a different material like the chemical or mechanical particles inside of this slurry. So after this process, we can have some slurry residue. The swirl scratch is very common. It's the swirl shape, and some micro scratch. We will definitely get particles, and if the pad is not optimized, we can get some edge rings. So actually in practical, those signature defects like the scratch here or the edge rings here, they are a very good way to monitor this CMP tool, and this is a very good way to optimize the pad. So after those things, now is the time we want to see the defects. There are so many defects on the wafer and throughout the different processes. We want to see where they are. And also we cannot do anything if we cannot see it. So the most common way to see the defects is by optical inspection. So there are bright field or dark field optical. It's you can say it's an optical microscope. You can either think about the light is imaging the whole, or is looking at the whole wafer, or is looking at a small portion of the wafer, and then you scan it by moving the wafer back and forth. Here is a picture of the inspection tool. You have this wafer here, and it's moving back and forth. You can scan, you can look at a small portion and then scan this whole wafer really quickly. So also here is a very typical map of the wafer. So you have the scratch lines, some of the scratch lines, some at the edge, maybe the slip lines, some large particle here, and small particle here and there. So many different of them. So the good advantage of the optical inspection is it's non-contact. You can see there's nothing, it's just light shooting on top of there. So it's non-contact, non-destructive, and can have a really high throughput. But the disadvantage is because we are using visible light or maybe deep UV light or even EUV light, those light has relatively long wavelengths, and it's really hard to get down to the resolution to see the really small particle. And also it's going to be hard to classify the defects. It's really hard to resolve those defects and classify. A different way is to use E-beam. The electron has much shorter wavelengths, which can give us enough resolution. And we saw before, most of the image I showed before is from the SEM picture. So those can really give us a very nice image and see the shape and like location, etc. Of the defect. Give us much better way. But the disadvantage, of course, is the throughput. You can only see very small, tiny area, and if you want to see the whole wafer, it takes forever. Also, because the SEM image is a contact method, is also disadvantage compared with optical inspection. Also, to point out, because we said before, if we have an error in the mask, the error will reproduce on every single chip. So mask inspection is also very important. And finally, the challenge. So I want to see. So the challenge for the defect inspection is because the defects is getting smaller and smaller. So it's really hard for no matter optical inspection or E-beam inspection, for them to see smaller and smaller features. And also, if we are using one single method to do the inspection, it might be limited with the wavelengths. For example, here, with the E-beam, you can see a clear something here, but with a EUV light, you cannot see anything. Similarly, if you see with a visible light or a deep UV light, and you might not be able to see it with a different wavelength. So it can be wavelength sensitive. And also, as the transistor goes to 3D, so the 3D inspection is a new challenge for defects inspection. So for how to resolve them, the first thing is in 1960, the clean room is introduced because we want to minimize the particle in the environment. An additional process is introduced to remove the contamination. There's a very famous one, RCA clean. So it can clean, it can remove the organic contaminant, oxide layer, and ionic contamination. So there's some also optical correction and maybe E-beam correction we can do after we see the defects, and we can repair those parts and make the chip still usable. So a better way is maybe we can control the process to make a defect-free process 2 or a defect-free wafer. So there are many ways, but they are not that easy. Overall, the most important thing we want to have is to have the chip working and improve the yield. Good, thank you for watching.